Welcome! Today, we'll be exploring problem number 1928, titled Minimum Cost to Reach Destination in Time. In this problem, we'll tackle how to determine the minimum cost to travel between nodes within a given time constraint. Let's dive in and uncover the best solutions. In this problem, we are working with a weighted, undirected graph represented as an array called edges. Each element in edges describes a connection between two cities, where edges, I equals U V, time underscore I, means there is a road between city U and city V that takes time underscore I minutes to travel. Along with this graph, we are given an integer max time, which is the maximum time we are allowed to spend traveling. Additionally, there is an array called passing fees, where each element passing fees, J, represents the cost of passing through city J. Our task is to determine the minimum cost required to travel from city 0 to city N1, such that the total travel time does not exceed max time. If it is not possible to reach the destination within this time limit, we must return -1 as the output. Now let's look at an example to better understand the problem. Suppose we have edges equals 0, 1, 10, 1, 2, 10, 0, 2, 1, max time equals 10, and passing fees equals 5, 2, 1. Here, the graph consists of three cities connected by roads with specific travel times. To solve this, we start at city 0 with a passing fee of 5. From city 0, we can take the direct path to city 2 using the edge 0, 2, which only takes 1 minute. Adding the passing fee for city 2, which is 1, gives a total cost of 5 plus 1 equals 6. Since this path is within the time limit of 10 minutes, the answer is 6. In another example, suppose we use the same graph but set max time equals 5 and keep passing fees equals 5, 2, 1. Here, it is impossible to reach city 2 from city 0 within the time limit of 5 minutes. The shortest direct path between city 0 and city 2 takes 1 minute, but no other paths that might allow us to reach the destination exist within this time constraint. As a result, the output in this case is -1, indicating that reaching the destination is not feasible within the given time. In a third example, let's consider edges equals 0, 1, 5, 1, 2, 5, 0, 2, 10, max time equals 10, and passing fees equals 1, 2, 3. Here, we start at city 0 with a passing fee of 1. From city 0, we travel to city 1 via the edge 0, 1, which takes 5 minutes and adds a passing fee of 2. From city 1, we continue to city 2 using the edge 1, 2, which also takes 5 minutes and adds another passing fee of 3. The total time spent is 5 plus 5 equals 10 minutes, which is within the allowed time limit. The total cost is 1 plus 2 plus 3 equals 9. This is the minimum cost path that satisfies the constraints, so the output is 9. When solving this problem, there are several constraints and edge cases to consider. For example, the number of cities, n, ranges from 1 to 100, and the number of edges can be up to 10,000. Each edge is described by three integers, u, v, time underscore I, where u and v are valid city indices, and the time required to traverse the edge, time underscore I, ranges from 1 to 1000. The passing fees for cities also range from 1 to 100,000. Some important edge cases include disconnected graphs, where it is impossible to reach city N1 from city 0, resulting in an output of -1. If the time limit is very tight, it might not be feasible to reach the destination even if paths exist. Additionally, graphs may have multiple paths with the same cost or even self-loops, which should not affect the shortest path calculation. Lastly, if there are no edges in more than one city, the output should be -1 since no path exists between the cities. To begin analyzing the problem, we first considered a brute force approach that uses depth-first search, or DFS. The intuition here is straightforward: explore all possible paths from the source node to the destination node. For each path, we keep track of the cumulative cost in time, and if we reach the destination within the allowed time limit, we record the cost. The result would be the minimum cost among all valid paths. However, there are critical limitations to this method. First, it is extremely slow for large graphs because it explores all possible paths without any optimization. For a graph with n nodes and e edges, the number of potential paths can grow exponentially in the worst case. This results in exponential time complexity, and the space complexity is linear, O, n, due to the recursion stack. Ultimately, we rejected this approach because its exponential time complexity renders it impractical for graphs of significant size or when strict time constraints are applied. Instead, we shifted focus to an optimized approach that combines dynamic programming with Dijkstra's algorithm. The key insight here is to reframe the problem as a constrained shortest path problem. We aim to find the path with the minimum cost to the destination while ensuring the total travel time remains within the allowed limit, max time. To achieve this, we adapt Dijkstra's algorithm to minimize cost rather than distance, and we augment it with dynamic programming to handle the time constraint. Specifically, we maintain a priority queue that always processes the path with the current minimum cost. Additionally, we use a DP node time table where each entry represents the minimum cost to reach a particular node within a given time. If a path exceeds the time constraint, we prune it early to avoid unnecessary computation. The algorithm proceeds by iterating through the neighbors of each node, calculating the new cumulative time and cost, and updating both the DP table and priority queue whenever a better path is found. This approach ensures that we focus only on feasible paths and avoid redundant calculations. Analyzing the complexity of this optimized method, the time complexity is O, n plus e, asterisk max time, where n is the number of nodes, e is the number of edges, and max time is the maximum allowed travel time. This arises because each node and edge is processed multiple times, up to the number of possible time states. The space complexity is O, n asterisk max time, as we need to store the DP table, which tracks the minimum cost for each node and time combination. We selected this strategy due to its balanced trade-off between efficiency and feasibility. By leveraging a priority queue, the algorithm prioritizes paths with the lowest cost, ensuring it doesn't waste time on suboptimal routes. The dynamic programming table further enhances efficiency by preventing redundant calculations and ensuring that all paths within the time constraint are considered. This makes the approach highly practical for solving the problem within competitive programming constraints. Finally, let's consider the trade-offs and comparisons between the brute force and optimized approaches. The brute force method, while conceptually simple, is computationally infeasible for large graphs due to its exponential time complexity. In contrast, the optimized approach incorporates structured search and pruning, making it significantly more efficient. However, this efficiency comes at the cost of slightly increased implementation complexity, as it requires the integration of Dijkstra's algorithm with dynamic programming. Despite this, the efficiency gain makes it well suited for competitive programming and real-world applications. Ultimately, we chose the optimized approach because it strikes the right balance between correctness and performance. It guarantees the optimal solution within the given constraints while avoiding the inefficiency of the brute force method. This ensures that we can solve the problem effectively without exceeding computational limits. In this problem, we are tasked with finding the path from a source node to a destination node in a weighted graph that has the minimum cost, while ensuring that the total travel time doesn't exceed a given time limit. If no such path exists, the solution should return -1. To solve this, the first step is to represent the graph using an adjacency list. This is a compact and efficient way to store graph data. Each node in the graph will have a list of tuples, where each tuple represents a neighboring node, the cost to travel to that neighbor, and the time it takes to do so. For example, if there is an edge from node U to node V, with a cost of C and a travel time of T, we would represent it as graph U.append V C T. This structure will allow us to efficiently access all neighbors of a node during traversal. To explore all possible paths in the graph, we can use depth-first search or DFS. This brute force approach systematically traverses the graph, checking every potential path to find the one with the minimum cost that satisfies the time constraint. The traversal is implemented recursively. At each step, the algorithm adds the cost and time of the current edge to running totals. If the cumulative time exceeds the time limit, the algorithm prunes this branch and backtracks to explore other options. When the destination node is reached, the algorithm compares the current path's cost to the smallest cost found so far and updates it if the current cost is lower. To support this process, we initialize key tracking variables, min_cost, which keeps track of the smallest valid cost, and a visited array to ensure that cycles are avoided by marking nodes already traversed in the current path. The core of this approach is the recursive DFS function. This function accepts parameters such as the current node, the cumulative cost and time, and the visited array. The base case occurs when the current node is the destination. Here, we check if the cumulative cost is lower than the minimum cost found so far and update min_cost accordingly. For the recursive case, the algorithm iterates through all neighbors of the current node. If a neighbor hasn't been visited and the new cumulative time remains within the time limit, we mark the neighbor as visited and make a recursive DFS call. After exploring all paths from this neighbor, we backtrack by unmarking it as visited, ensuring that other potential paths remain unaffected. Additionally, the algorithm handles edge cases, such as when no valid path exists, by checking if min_cost remains unchanged and returning -1 in that scenario. It also ensures robustness for disconnected graphs, where not all nodes are reachable. There are several key insights that make this algorithm effective. First, DFS is a natural choice for this problem because it systematically explores all possible paths while keeping track of cumulative cost and time. This allows us to prune paths early when they exceed the time limit, significantly reducing the number of paths that need to be considered. The use of backtracking ensures that cycles are avoided, and each path is explored independently. Furthermore, the algorithm is designed to handle edge cases explicitly, such as returning -1 when no valid path exists. Overall, these strategies enable the DFS approach to efficiently find the optimal solution while gracefully handling invalid scenarios. The algorithm relies on key data structures to achieve efficiency. The adjacency list is used to represent the graph compactly, allowing for quick access to a node's neighbors in O1 time. A visited array is critical for tracking nodes in the current DFS call, ensuring that cycles are avoided. Additionally, tracking variables like min_cost and cumulative counters for cost and time allow the algorithm to maintain state as it traverses the graph. When it comes to complexity, the time complexity is O(V*E), where V is the number of nodes and E is the number of edges. This accounts for the worst-case scenario where all paths are explored. The space complexity is O(V), driven by the recursion stack and the visited array. These choices balance the need for thorough exploration with efficient resource usage. To solve the problem, we first import the necessary modules, heap for managing the priority queue and defaultIct for creating our graph representation. Next, we define the min_cost method within the solution class. Our goal is to calculate the minimum cost to reach the destination within the given time limit. For this, we start by building the graph as an adjacency list, where each node is connected to its neighbors with their respective travel times. This is achieved through the loop that iterates over the edges list and populates the graph. Once the graph is ready, we initialize a priority queue, PQ, to facilitate a Dijkstra-like search. Each entry in the queue is a tuple containing the current cost, the current time, and the current node. Initially, we start from node 0 with its corresponding passing fee as the cost, a time of 0, and the node itself. Additionally, we maintain a min_time dictionary to track the minimum time required to reach each node at a given cost. For now, we set the minimum time to reach node 0 as 0. The priority queue is processed in a while loop. At each step, we pop the node with the lowest cost. If this node is the destination, we return the cost immediately, as we found the optimal path. However, if the time required to reach this node exceeds the max time, we skip further exploration for this path. Now, we explore the neighbors of the current node. For each neighbor, we calculate the new time and cost required to reach it. The new _time is the sum of the current time and the travel time to the neighbor, while the new _cost is the sum of the current cost and the passing fee for the neighbor node. To ensure we're only considering valid paths, we check if the new time is within the max time and if this path offers a faster time to reach the neighbor compared to any previously explored paths. If these conditions are satisfied, we update the min_time for the neighbor and push the new path, represented by the tuple new_cost, new_time, neighbor, into the priority queue for further exploration. Finally, if the priority queue is exhausted and we have not returned a cost, it means there's no valid path to reach the destination within the given time. In this case, we return -1 to indicate that no solution exists. This ensures that our algorithm handles all possible scenarios in a clear and efficient manner. Here, we start by defining the min_cost method that takes the maximum allowed time, the edges of the graph, and the passing fees as inputs. The first step is to build the graph using an adjacency list, where each node is mapped to a list of its neighbors along with the travel time to reach them. This is achieved using a hash map and by iterating through the edges. Next, we initialize a priority queue to facilitate a Dijkstra-like search. The queue is sorted by cost, and we begin by adding the starting node with its passing fee as the initial cost, 0 time, and node index 0. We then create a hash map, min_time, to track the minimum time required to reach each node. Initially, we set the time for the starting node to 0. Now, we enter a loop where we process nodes from the priority queue. Each entry in the queue contains the current cost, time, and node. If the current node is the destination, we return the accumulated cost as the result. If the current path takes more time than the allowed maximum, we skip processing it further. Otherwise, we explore the neighbors of the current node. For each neighbor, we calculate the new time and cost to reach that neighbor by adding the travel time and its passing fee to the current values. We only consider this new path if it is within the time limit and represents an improvement over previously recorded paths to that neighbor. In such cases, we update the min_time map with the new time for the neighbor and add this path to the priority queue for further exploration. If the queue becomes empty and we haven't reached the destination, it means no valid path exists within the given constraints, so we return -1. This completes the implementation of the algorithm, ensuring that we find the minimum cost to reach the destination within the allowed time or determine if it's not possible. To start solving this problem, we take the given input values. Here, we have a maximum allowed time of 30 edges that connect the nodes with specific travel times, and passing fees for each node. First, we construct the graph using an adjacency list. This representation makes it easy to see which nodes are connected and the time it takes to travel between them. For example, node 0 is connected to node 1 with a travel time of 10, and to node 2 with a travel time of 20. Next, we initialize a priority queue with the starting node, which is node 0. The queue starts with a tuple containing the current cost, time, and node 5, 0, 0, since the cost of entering node 0 is 5 and the time spent so far is 0. We also maintain a dictionary to track the minimum time required to reach each node, starting with 0, 0. Now at node 0, we explore its neighbors. For node 1, the new time becomes 10, and the new cost becomes 15. This is added to the priority queue. Similarly, for node 2, the new time is 20, and the new cost is 25. After these updates, the priority queue contains two entries, 15, 10, 1, and 25, 22. Next, we process the node at the top of the priority queue, which is node 1 with a cost of 15 and time of 10. At node 1, we explore its neighbors. For node 0, the new time becomes 20, and the new cost becomes 20. However, we skip this path since we've already reached node 0 in less time, as recorded in the min_time dictionary. For node 2, the new time is 20 and the new cost is 35. But we skip this path because the cost is higher than an existing path to node 2. With no further valid updates, the priority queue now contains only one entry, 25, 22. Processing node 2, we pop it from the queue. Since this is the destination node, we return the cost of 25, which is the minimum cost to reach the destination within the given constraints. Now, consider a case where no valid path exists. Here, the maximum allowed time is 15, and the graph structure remains the same. We start by constructing the adjacency list, which shows the connections and travel times between nodes. After this, we initialize the priority queue with node 0, 5, 0, 0, and set up the min_time dictionary with 0, 0. At node 0, we explore its neighbors. For node 1, the new time becomes 10, and the new cost is 15. This is added to the priority queue. For node 2, the new time becomes 20, but we skip this path since it exceeds the maximum allowed time of 15. With these updates, the priority queue contains only 15, 10, 1. Next, we process node 1 from the priority queue with a cost of 15 and time of 10. At node 1, we explore its neighbors. For node 0, the new time becomes 20, but this exceeds the maximum allowed time, so we skip this path. Similarly, for node 2, the new time becomes 20, which again exceeds the maximum allowed time. With no valid paths, the priority queue becomes empty, indicating that there's no way to reach the destination within the allowed time. As a result, we return -1 to signify that no valid path exists. In this example, the graph is slightly more complex, and the maximum allowed time is 50. The graph consists of 4 nodes, with connections and travel times as specified. First, we construct the adjacency list, which shows that node 0 is connected to nodes 1 and 3, and so on. We initialize the priority queue with node 0, 5, 0, 0, and set up the min-time dictionary with 0, 0. At node 0, we explore its neighbors. For node 1, the new time becomes 10, and the new cost is 15. This is added to the priority queue. For node 3, the new time becomes 40, and the new cost is 25. After these updates, the priority queue contains 15, 10, 1, and 25, 40, 3. Next, we process node 1 from the priority queue with a cost of 15 and time of 10. At node 1, we explore its neighbors. For node 0, the new time becomes 20, but we skip this path since there's already a faster path to node 0. For node 2, the new time becomes 20, and the new cost is 30. This is added to the priority queue. With these updates, the queue now contains 25, 40, 3, and 30, 22. Processing node 2 next, we explore its neighbors. For node 1, the new time becomes 30, but this path is skipped as it's slower than an existing path to node 1. For node 3, the new time becomes 30, and the new cost is 50. This is added to the priority queue. Finally, we process node 3 from the queue with a cost of 25 and time of 40. Since we've reached the destination, we return 25 as the minimum cost to reach the destination within the given constraints. To analyze the time complexity of our solution, we start by breaking it into 2 main parts. First, we consider graph construction. The input edges list contains edges, and constructing the adjacency list requires iterating through each edge. Since processing each edge takes constant time, the time complexity for this step is O(E). Next, we focus on the Dijkstra-like search. Here, the priority queue is designed to explore nodes in increasing order of cost. In the worst-case scenario, we might process every node and edge multiple times due to different combinations of cost and time. Let's denote the number of nodes as V. For each node, it's possible to maintain up to max time states, as we track different time states for that node. This means the total number of states pushed into the priority queue can go up to O(V*max time. For each push or pop operation in the heap, the time complexity is O log S, where S represents the number of states in the heap. Since S can grow to O(V*max time, each heap operation takes O log V*max time. Additionally, exploring all neighbors of a node requires O(E) time as we iterate through the edges. By combining these factors, the total complexity for the Dijkstra-like search becomes O(V*max time log V*max time plus E. Now, let's summarize the overall time complexity. The graph construction step takes O(E), and the Dijkstra-like search contributes O(V*max time log V*max time plus E. When we combine these, the total time complexity is O(V*max time log V*max time plus E. Next, we analyze the space complexity. First, the adjacency list, which represents the graph, requires O(E) space. This is because each edge is stored twice, once for each direction in an undirected graph. The priority queue is another key component. In the worst case, it can hold up to O(V*max time states, where each state contains information about cost, time, and the node. Since each state requires O(1) space, the total space for the priority queue is O(V*max time. Lastly, the min_time dictionary is used to map nodes to their minimum time values. This dictionary can store up to O(V) entries in the worst case, as there is 1 entry per node. Therefore, the space complexity for the dictionary is O(V). Moving to the overall space complexity, we combine the contributions from the adjacency list, priority queue, and min_time dictionary. The adjacency list takes O(E) space, the priority queue takes O(V*max time, and the dictionary takes O(V). Adding these together, the total space complexity is O(E) plus V*max time. To put this in perspective, let's compare the optimized approach to a brute force method. A naive solution would explore all possible paths from the source node to the destination while tracking cost and time. This would lead to a combinatorial explosion of possibilities, resulting in exponential time complexity. By contrast, the optimized solution uses a Dijkstra-like algorithm with a priority queue. This approach efficiently prioritizes paths with lower costs and prunes paths that exceed the max time constraint. As a result, the algorithm avoids unnecessary computations and performs well even on large inputs. Finally, let's analyze the algorithm under different scenarios. In the best case, the shortest path to the destination is found early, reducing the number of states that need to be explored. However, graph construction is still required, so the best case time complexity is at least O(e). In the average case, the algorithm explores a moderate number of states before reaching the destination. The complexity in this scenario is close to the worst case but may involve fewer iterations depending on the graph structure. In the worst case, the algorithm has to explore every node and edge multiple times due to various combinations of cost and time. This results in the full complexity of O v *maxtime log v *maxtime plus e. The worst case occurs when the graph is densely connected, maxtime is large, and many paths need to be evaluated before finding the optimal one or concluding that no valid path exists. When tackling graph problems, there are some common mistakes you should watch out for. First, forgetting to account for cycles in the graph can lead to infinite loops or revisiting the same nodes unnecessarily. This is why it's important to use a visited set or similar mechanism to track the nodes you've already explored. Next, ignoring edge cases is a frequent pitfall. For example, your solution might fail on empty inputs, single-node graphs, or disconnected components. Testing with these special cases ensures your solution is robust. Another mistake is overcomplicating the solution. Instead of jumping to a complex approach, consider whether something simpler, like BFS, might work just as well. Additionally, incorrect base cases in recursive algorithms can cause stack overflows or incorrect results, so always double-check that your termination conditions are properly defined. Finally, misjudging time or space complexity can lead to solutions that perform poorly or exceed limits. Carefully analyzing constraints can help you optimize your solution effectively. In interviews, recognizing patterns is a key skill. Many graph and pathfinding problems follow common patterns, such as using BFS for shortest paths or DFS for exploring all possible paths. Spotting these patterns can significantly reduce the time it takes to devise a solution. It's also important to aim for the optimal approach right away, as interviewers often prioritize efficiency over brute force methods. If you have multiple potential solutions, discussing their trade-offs can demonstrate your understanding. For instance, BFS is usually better for shortest path problems, while DFS is more suited for exhaustive searches. Once you've implemented a solution, running through test cases, especially edge cases, can validate its correctness and robustness. If you've encountered a similar problem in the past, referencing it can highlight your broader experience and ability to draw connections between problems. Graph problems often share similarities with related challenges. For example, LeetCode 200, number of islands, is a classic problem for practicing DFS or BFS traversal. LeetCode 797, all paths from source to target, involves backtracking to explore all possible paths. LeetCode 743, network delay time, is a shortest path problem where Dijkstra's algorithm can be applied. And LeetCode 133, clone graph, requires careful handling of visited nodes during graph traversal. When approaching these problems, it's helpful to understand alternative strategies. For instance, while DFS is memory efficient, BFS guarantees the shortest path in unweighted graphs. Similarly, Dijkstra's algorithm is faster for non-negative weights, whereas Bellman-Ford works with negative weights but has higher time complexity. Backtracking is useful for exploring all possible paths, though it can be computationally expensive, so pruning can help optimize it. Dynamic programming is another powerful tool, especially when problems involve overlapping subproblems, such as in Floyd-Warshall for all pairs shortest paths. To excel in graph problems, it's crucial to recognize that they often require a mix of traversal techniques and optimization strategies. Identifying the right combination early on can guide you toward an effective solution. Time complexity analysis is especially important for problems with large constraints. You need to ensure your solution scales efficiently. During an interview, discussing edge cases and constraints demonstrates that you're thinking critically about the problem. This shows a thorough and thoughtful approach, which is something interviewers value highly. By combining these insights with solid problem-solving techniques, you can tackle graph problems confidently and effectively. Great work! To wrap up, we tackled the problem of finding the minimum cost within time constraints. We discussed the brute force DFS approach and highlighted its trade-offs. Remember the key concepts of graph traversal and optimization strategies. Thanks for watching, and see you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!